All right, so today we are going to look at simplifying roots. You'll see in the second half of chapter 4 we deal with a lot of square roots, and so we need to look at how do we simplify them. Remember that you need to know your perfect squares. All right, so if you don't remember them, I would jot some down on the sides. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4. The square root of 25 is 5. The square root of 36 is 6. The square root of 49 is 7. The square root of 64 is 8. The square root of 81 is 9. And the square root of 100 is 10. Now, there are some more. The square root of 121 would be 11. The square root of 144 is 12. The square root of 169 is 13. The square root of 196 is 14. And the square root of 225 is 15. Now, it keeps going, but for the most part, those are the ones you'll see most often. So we're going to look at several different types of expressions, I should say, involving radical symbols or square root signs, and how do we simplify them. The first one says the square root of 80. What we want to do, since 80 is not one of my perfect squares, we want to look for two numbers that multiply to be 80, where one of those numbers is a perfect square. So the rule that we're using is this idea that the square root of a product can be split up, and we can take the square root of each piece individually. So we need to look at factors of 80. So we have 1 and 80, we have 2 and 40, we have 4 and 10, 8 and 10. We have 5 and 16. So 16 is a perfect square. That would be a nice one to break this into. So instead of the square root of 80, we're going to think of it as the square root of 16 times the square root of 5. The square root of 16 is perfect. Its root is 4. So this is going to come out as a plain 4. And then the 5 is not perfect, so we leave that inside the square root symbol. It's always best if you can put your perfect square in the first position here so that it's going to come out and be right in front. It's always the one that's perfect that comes out of that root symbol. Now, 288. Again, we're looking for a perfect square that goes into 288. It's best if you can find it, the largest one, right away. So if you look at our numbers here, 225, 288 would be a little beyond that. Let's find one of these numbers that goes into 288. And if we look here, 144 can be divided out of this 2 times. So the square root of 288 would be 144 times the square root of 2. Square root of 144 is 12, so we end up with a 12 root 2. Now let's say we didn't find the largest one. Let's say we looked at that 288 and we said, what's a number that goes into it, a smaller number? Well, we can split it into 4. 4 goes into 28 7 times and into 8 twice. And that would help us because the square root of 4 is perfect. However, when we pull that 2 out of the square root of 4, we're still left with the square root of 72, which has a perfect square inside it. So if we were to break down 72 into 36 times 2, this front 2 is still going to be part of it. The 36, when we square root it, becomes a 6, and that 2 is still inside because it's not perfect. And 2 times 6 would be 12, so we end up with the same answer, but notice it took us a lot more steps to get to that answer. So if you can find the largest perfect square that goes in there first, that would be best. One technique you can use for larger numbers is to divide by small numbers like 2, 3, 5, and see if it's paired with a number that is perfect. All right. Let's look at this one. 5 times the square root of 48, number 7 here. 5 times the square root of 48. Now this one has a number that's not inside a root in front. We still have a square root of a number that can be broken down. We need a perfect square that goes into 48. So again, if we look at our numbers, 49 is perfect. Start working your way down. Does 36 go into 48 evenly? No. Does 25 go in evenly? No. Does 16 go in evenly? Yes. It goes in 3 times. Now remember that 5 that's in front is still going to be sitting in front. The square root of 16 comes out as a 4, and that 3 is not perfect, so it stays inside. And then those two numbers that are outside of our root can be multiplied together. So 5 times 4, we'd get 20 square roots of 3 for our answer. Now our next question, we have a negative 2 times the square root of 90. Again, we're looking for a perfect square that goes into 90. We could use 9 times 10. 9 is perfect. There's still the negative 2 in front. The square root of 9 becomes a 3. And the square root of 10 is not perfect, and it doesn't have any perfect square factors that would help us break it down. Our simplified answer, if we put the negative 2 times 3 together, as a negative 6 times the square root of 10. All right, let's look at number 9 here. I see that we have some duplicate numbers. I'm not sure how that happened. All right, question 9. We have 7 times the square root of 8, and we're multiplying that to negative 3 times the square root of 12. Now, one of our rules is that we can multiply the numbers together if they're both outside of the root, or we can multiply the numbers together if they're both inside the root. So we're going to take the 7 and the negative 3 and multiply that together as negative 21. And then we're going to multiply the root pieces back together. Because 8 and 12 are not perfect, it doesn't help me to have them split up that way. The square root of 8 times the square root of 12 becomes the square root of 96. And now I can try to split it up in a different way. All right, we need factors of 96, and we need one of them to be perfect. So going back to our list here, 96, if it were perfect, would be between 81 and 100. We're going to work our way down. Does 81 go into 96 evenly? No. Does 64? No. Does 49? No. Does 36? No. Does 25? No. Does 16? Yes. 16 can go into 96 6 times. So now we have a negative 21, we have a square root of 16, and a square root of 6. The square root of 16 is a 4. The square root of 6 is not perfect. We're going to leave it inside. And now when we multiply the numbers that are out front, that are outside of our square roots, negative 21 times 4, we'd get negative 84 square roots of 6. All right, question 10. We have negative 3 root 2 times negative 3 root 50. Again, if we multiply the pieces that are outside together, we get a positive 9. And if we multiply the pieces that are inside together, 2 times 50 is 100. Now 100 is a perfect square. Its root is just a 10. So this becomes 9 times 10, which would simplify down to just being 90. All right, our next question. We have 2 times the square root of 7, and then there's that 2 on the outside. That means we really have 2 of the same thing. So picture taking 2 root 7 times itself. We can multiply the 2's together to get a 4. We can multiply those 2 root 7's together to get the square root of 49. But the square root of 49 is just a 7. So 7 times 4 would simplify to be 28. All right, let's take a look at number 13. Notice here that we have a numerator that has a plain number and a square root number. Before we can do any kind of dividing, we need to break down that square root. So we have 5 plus the square root of 75. We're going to think of 75 as being 25 times 3. So we can think of that as the square root of 25 times the square root of 3. And the square root of 25, that is perfect. That's going to come out as just a plain 5. So we end up with 5 plus 5 root 3, all divided by 5. Now when you are dividing a numerator that has several pieces by this 5, we have to think of dividing each chunk by the 5. So 5 divided by 5 would get us a 1. And then if we look at the second part, we have a 5 root 3 divided by 5. Just like with multiplying, we can divide if the two numbers are outside of the square root. In this case, those two 5s, we could divide them and get a 1. So we end up with just 1 root 3. So 1 plus a square root of 3 would be our answer. Let's try another one of those. Let's look at number 15. We have negative 15 plus the square root of 63, and we're dividing by 12. So let's think of that 63. We could break that into 9 times 7. So we end up with a negative 15 plus the square root of 9 would just be a 3. We still have the root 7 left. And now we're dividing this all by 12. Well, 12 doesn't go into negative 15 and 3 evenly, but there is a number that we could divide out of both. We could divide 3 out of everything. So if we divide the negative 15 by 3, we get negative 5. If we divide the 3 root 7 by 3, we get a root 7. And if we divide the 12 by 3, we get a 4. So as long as we can divide it out of all the pieces, then we can go ahead and reduce that. All right, let's look at the back page. Let's start with question 21. Now notice on these, we still have a fraction, but this time we have a single numerator and we're dividing by a number that's inside a radical. We have to do something called rationalizing the denominator. We don't want square roots in the denominator. So what we want to do is we want to multiply by something that's going to make the denominator perfect so that we can take the root of it. So if I have the square root of 3 and I multiply it by another root 3, I'm going to end up with the denominator that's the square root of 9, and that's perfect. Whatever I multiply to the denominator, I also have to multiply to the numerator. So the numerator becomes 5 times the square root of 3. Notice that does not become the square root of 15. The 5 is outside the root and the 3 is inside. We can then reduce the denominator to being just a plain 3. And we can't reduce the 5 and the 3. There's no common factors there, so that would be as simplified as we could go. For question 22, notice that both the numerator and denominators are in square roots. Just like with multiplying, we said that the square root of a times b can be broken up into the square root of a times the square root of b. Well, the same thing works with fractions. We can take the square root of a divided by the square root of b and think of it being the square root of the fraction a divided by b. So since both of these are inside a square root symbol, I want you to think of it just being one big square root over all of it. And the reason I'm doing that is because 5/10 can be reduced. We can think of that as just a 1/2. So that's going to make this a little easier to rationalize if we think of it in its reduced form first. So now I have the square root of 1, which is a 1. I'm dividing by the square root of 2. To rationalize this, I have to make the denominator perfect. If I multiply it by another root 2, my denominator becomes the square root of 4, which is perfect. It's just a plain 2. Whatever I multiply to the denominator, I also have to multiply to the numerator. So I get 1 times the square root of 2, which would just be the square root of 2. So my reduced answer would be the square root of 2 divided by 2. All right, let's look at question 25. This time we cannot reduce those because that first 5 is not inside a square root, and there's a plus sign in between the two terms. So we're going to have to leave it the way it is and rationalize it. To get the square root of 10 to be perfect, we're going to multiply it by another square root of 10. Again, what we do to the denominator, we have to do to the numerator. So when I look at the denominator now, root 10 times root 10 becomes the square root of 100, which is perfect, and it's going to give us just a plain 10. The numerator, I actually have to distribute. That root 10 is getting multiplied to the first number, that 5. So we get 5 root 10. Again, pay attention to that. It's not the square root of 50. It's just 5 times the square root of 10. When we multiply the root 10 times the root 5, that does become the square root of 50. Because both numbers were inside square roots, we can put them together. Now let's try to break down our square roots. There is nothing perfect in a 10, so we're still going to be left with 5 root 10. But we can break down the square root of 50. We can think of it as 25 times 2. And the square root of 25 is 5, so we end up with 5 square roots of 2. So now we're to the point of having 5 root 10 plus 5 root 2, all divided by 10. Since we can divide a 5 out of all three of those pieces, the red, the blue, and the green, we're going to go ahead and do that. So 5 root 10, if we divide out the 5, becomes just a root 10. 5 root 2, if we divide out of 5, becomes a plain root 2. And 10, if we divide by 5, just becomes 2. All right. We're going to look at 2 more. Notice on these last few that the denominator now is the one that has the 2 pieces. So let's look at number 27. I'm going to give myself a little more space here. So for question 27, to rationalize it when it has 2 pieces to the denominator, we have to use something called the conjugate. Conjugates have the same pieces, but opposite signs. So a plus b and a minus b are conjugates of each other. So what I need to do is use the conjugate of my denominator. So instead of 4 plus the square root of 5, I'm going to multiply by 4 minus the square root of 5. And again, whatever we do to the denominator, we have to do to the numerator. Let's simplify this a little bit. We're going to distribute. So we have a square root of 7 times 4. Again, one is inside and one is outside of the square root, so we cannot actually make that into a 28. We have to just leave it 4 times the square root of 7. When we distribute to the root 5, they are both inside a square root, so we can multiply them together inside. 7 times 5 is 35. For the denominator, we actually have a 2-piece term times a 2-piece expression, so we're going to think of foiling this out. 4 times 4 gets us 16. Outsides, we end up with a negative 4 times the square root of 5. Insides, we end up with a positive 4 times the square root of 5. And my last term, we've got the square root of 5 times a negative square root of 5. Positive times negative is negative. Root 5 times root 5 is root 25. Now, cleaning this up a little bit. For the numerator, there is a square root of 7. There's no factors that are perfect that go into 7, so it's going to stay 4 root 7. There's no factors of 35 that are perfect, so we have to leave that one as well. In the denominator, notice that we have a negative 4 root 5 and a positive 4 root 5. When we multiply those when we add those together, we get 0. The square root of 25 here is just a plain 5. And if we combine our like terms, 16 minus 5 would get us an 11. So we have 4 square roots of 7 minus the square root of 35, all divided by 11. We're going to try one more, question 28. All right, so we need to rationalize this using the conjugate of the denominator. So instead of 5 minus root 2, we're going to use 5 plus root 2. Whatever we multiply to the denominator, we also have to multiply to the numerator. Now for this one, we're going to have to FOIL both the numerator and denominator. So FOILing the top part, we have a root 2 times 5, so 5 square roots of 2. Outside, we get a root 2 times a root 2, which becomes root 4. Insides, we have 3 times a 5, so 15. And last, we have 3 times the square root of 2, so 3 root 2. We'll clean that up in a minute. For the denominator, FOILing this out, 5 times 5 is 25. Outsides, we end up with 5 times root 2. Insides, we end up with a negative 5 root 2. And our last term, we end up with negative times positive, so negative, and root 2 times root 2 is root 4. All right, we have some cleaning up to do here. First of all, notice that we have a square root of 4 here, which is just a plain 2. Same thing here, we have a square root of 4, that's a plain 2. We can combine pieces that have the same kind of term. So for the numerator, we can combine the 2 and the 15 to make a 17. We can also combine the 5 root 2 and add it to a 3 root 2 because they're both root 2's. So 5 root 2 plus 3 root 2, we get 8 root 2. For the denominator, notice that a positive 5 root 2 added with a negative 5 root 2 cancels out. So we're really just left with the 25 minus the 2, or 23. So our final answer is 17 plus 8 root 2, all divided by 23. Now, that was a lot of different types of questions that we looked at today. Hopefully, most of them are review from something you learned in Algebra 1. If you are struggling with any of them, please let me know, and we can do a Google Meet to discuss them before we move into the rest of Chapter 4.